We'll be talking about Chapter 5 today. Please take a few minutes to read through these terms to know and pause the slide for a minute. You might even want to look them up in your textbook, look up some definitions, and then we'll go on. Okay, I hope you looked up those terms and you have a little feel for what some of them mean. We're going to start out by talking about what food calories are. Food calories are the amount of energy in foods, and they can be measured not just in calories, but you could also measure them in joules. The abbreviation over here in the right column on this table stands for kilojoules per gram. The next column to the left is calories per gram, and then it gives some examples of each type of nutrient. These nutrients are also the macromolecules, the biomolecules that are found in our bodies. There's 4 major biomolecules. They are carbohydrates, proteins, fats, and nucleic acid. When our body goes through the process of cellular respiration, what we do is we take this energy from food and we convert it into usable energy that our body can use. That usable energy has to come in the form of ATP, and there are a lot of steps for our bodies to take this energy that's in food and convert it into the ATP, the usable energy for our bodies. We'll have more on that later when we get into our chapter on metabolism. This slide asks you a question. How many calories are contained in a food which has 6 grams carbohydrates, 3 grams fat, and 2 grams protein? Now there's one mistake in that question. This C should be a capital C for calories. That does make a difference, and I'll explain more about that on a later slide. So assuming that's a capital C calorie, and given that carbohydrates have 4 calories per gram, protein has 4 calories per gram, and fats have 9 calories per gram, take a moment, pause the recording, see if you can calculate how many calories there would be in this food. Okay, hopefully you did something like this. You took your 6 grams of carbohydrates times the 4 calories per gram for each gram of carbohydrates, and that gives you 24 calories from the carbs. You had 3 grams of fat. Each gram of fat contains 9 calories. Grams cancel out. That gives you 27 calories from fat. You have 2 grams of protein times 4 calories for each gram gives you 8 calories for the protein. Adding those together, I believe that comes to 59 total calories. So how do we use those 59 calories? Well, we do that through the process of cellular respiration, which is looked at in detail in Chapter 12. Cellular respiration takes our food, once it's converted down into its basic form of glucose. We breathe in oxygen. Our body goes through a series of complicated chemical reactions, converts that glucose and oxygen into carbon dioxide, which we breathe out, water, which we exhale and sweat off, and energy. This energy is in the form of what we call ATP, adenosine triphosphate, and again we'll look at that more in Chapter 12. We say that this is an exothermic reaction because energy is released in the reaction. Exo means out, so energy is given off in this reaction. Whenever you see this energy term on the right side of the chemical equation, that's going to be an exothermic reaction. In many reactions, there's a difference between the heat that's in the molecules of the reactants and the heat that's in the molecules of the products. We call this difference in heat the heat of reaction, and we call that enthalpy. Enthalpy is that difference between heat of reactants and products. So in the last equation, the products had less heat than the reactants because heat was given off. If you have a cold pack and put it on your skin, it absorbs heat from your skin. Your skin gets colder. That's an endothermic reaction because energy is being absorbed from the surroundings. This is the equation below is the equation for that cold pack. It shows the heat term on the left this time, and you have ammonium nitrate typically, which when it reacts with some water, when it dissolves in water, will convert into its ions. And when it does that, it absorbs heat from the surroundings. In order for those ions to be able to move apart, they need some more energy. Another way that we can represent this heat is to use the symbol delta H. This symbol here is a triangle, and triangle in physics and chemistry stands for change. So the change in heat in this reaction is 25 kilojoules per mole. That's the amount of heat needed for 1 mole of the ammonium nitrate to split up into its ions, ammonium ion and nitrate ion. So here's a little graphic of an exothermic and an endothermic reaction. In an exothermic reaction in the beaker here, you see that the heat is given off. So this beaker is hotter than the surrounding, the heat's going out to the surroundings. In an endothermic reaction, heat is going in, and this is cooler than the surroundings. Here's a better graphic, really an energy graph, so to speak, where we see that the energy of the reactants is less than the energy of the products. In an endothermic reaction, heat is taken in or absorbed to get to those products. In an exothermic reaction, the energy of the reactants is greater than the energy of the products, and so heat has to be given off in order to get to those products. Please take a moment and go through the following 4 questions. See if you think each one represents an endothermic or an exothermic process. Endothermic, heat being taken in; exothermic, heat being given off. When you're done, start the recording again, and you may be surprised on one of them at least. So take some time, write down your answers, and then restart the video, please. So here are the answers. Take a moment to check yours. Are there any that surprise you? I was thinking the first one might surprise you, because we think, well, the water gets colder, you know, and in an endothermic reaction, oftentimes temperatures decrease. Like if you are, for example, in the cold pack, the temperature of the ammonium nitrate would get colder as it absorbs heat from your skin. Well, in this case, the water freezing, what has to happen, it's a different type of process. If you think of taking a pan of boiling water and putting it into your refrigerator, into your freezer, put a pan of boiling water on top of your ice cream. What's going to happen to your ice cream? It'll melt. So that water has to be giving off heat. So the water actually is giving off heat to the surroundings. We always have to look at 2 things in these reactions: what's happening to the chemicals, what's happening to the surroundings. In the ammonium nitrate example, the chemicals were absorbing energy from the surroundings. They were surrounded by water, and they were absorbing energy from that water, which then absorbed energy from your hands, and that cold pack got cold. In this case, the water is the substance. It is giving off heat to its surroundings as its temperature goes down and the water freezes. So that's an exothermic reaction. In the next one, when sodium hydroxide is dissolved in water, it gives off its energy to the water, which then makes the beaker and the water hot. That's exothermic. It's easiest as number 3 if you have an energy term, because as you can see in number 3, the energy term is on the left. When we see the energy term on the left, we know it's an endothermic reaction. I'd like you to pause for a moment again and go back and look at the cellular respiration equation. The cellular respiration equation, compare it to this equation and see what you notice. So pause the video and then come back, please. Did you take a moment? You may have noticed that the cellular respiration is the exact opposite of this equation. So photosynthesis is the opposite of cellular respiration. In this equation, plants take in carbon dioxide and water and energy from the sun. They produce glucose and oxygen gas, which we then use for the reverse reaction of this. In number 4, because the products have more energy than the reactants, those products had to get that energy from their surroundings, so that would be an endothermic reaction. The total amount of energy that's absorbed or released in a chemical reaction has to do with the enthalpy, or the change in heat of the molecules, as well as the randomness of the particles. And we call that randomness of particles entropy. So instead of exothermic and endothermic, sometimes chemists use the terms exergonic and endergonic, but they mean essentially the same thing as exothermic, endothermic. In an exergonic reaction, the total amount of energy, the heat of reaction plus the amount of disorder, the entropy, results in the products having less energy than the reactants. Endergonic is opposite. The products will have more energy than the reactants. When we get into Chem 120, a higher level of chemistry, we'll talk about something called Gibbs free energy, and that's represented by this delta G here. Basically, if that energy is less than 0, then you have an exergonic reaction, and we say that that reaction is spontaneous. If that energy is greater than 0, then it's an endergonic reaction, and the reaction is not spontaneous. Now, it's not important that you know Gibbs free energy, but what is important is that you understand the difference between a spontaneous and a non-spontaneous reaction. A spontaneous reaction will go on by itself. A non-spontaneous reaction requires energy in order for it to happen, a continual flow of energy. For a chemical reaction to occur, the molecules have to have enough activation energy so that they can align properly and then break apart and reform. We'll talk more about this in a little bit. You might remember Lab 2, where you decomposed water into its elements, oxygen and hydrogen. When you did that, you had a beaker of a container of water, and you took a little battery, and you had 2 thumbtacks on the bottom of the cup that the water was in, and you put a little bit of baking soda in there to make it conduct the electricity better, and then you put a couple of test tubes in, and when your battery was running, gas was given off. One of the test tubes collected hydrogen, the other collected oxygen. That's an example of a non-spontaneous reaction because you had to keep supplying the energy in order for that reaction to happen. If you took the battery away, then those bubbles quit forming. Spontaneous reaction, on the other hand, happens all on its own, and we didn't do the one that's mentioned here on the slide, but you can take sucrose or table sugar. Actually, I can do this because it would be difficult for you to get the materials to do this, but if I take table sugar and add some concentrated sulfuric acid to it, it will decompose into carbon and water. And it's a really cool reaction, so I put a link here so that you can watch that reaction. You have to be a little bit patient because it takes a while for the cool stuff to happen. It's a slow reaction, but the video gets good towards the end. Another video link that I put here is a link on electrolysis, but in this case the chemist is using sodium hydroxide and decomposing it into first hydrogen and then oxygen and sodium metal. So they're extracting the sodium metal from the sodium hydroxide. Sodium metal is very dangerous. It will explode because it can create hydrogen gas with water, and the hydrogen explodes. It burns on contact with water. If you tried to hold it in your hand, it would start on fire and possibly explode. So it's always stored under oil or something similar, kerosene, something like that. So when you watch this video, please, please, please never try this at home. It's extremely dangerous, but it's a good video to show you what electrolysis can do and how dangerous the metal sodium is and how different it is from table salt, sodium chloride. So reactions can be spontaneous or non-spontaneous, and we also can talk about the rate of reaction, how quickly the reaction happens. The reaction on the left side of this slide has a slow rate. It takes a while for the purple and yellow particles to make the brown one. The reaction on the right side has a much faster rate. By the time you get down here to 30 seconds on the timer, all of the red and blue have changed into green. Reactions happen because molecules collide. So if you can make those molecules collide more quickly, then you will have a quicker rate of reaction. Some things that we can control in order to make that happen are things like temperature, concentration of particles if you have a solution or a gas, amount of surface area of a solid, and then something called a catalyst. In general, anytime you have more collisions, then you'll have a quicker reaction. So if you have a more concentrated solution, that means that you'll have more particles in a smaller area, and you will have a faster rate of reaction. If you increase the temperature of your reaction, then your particles will move faster. Faster moving particles will collide more frequently, so the reaction rate will be higher. If you can increase the surface area of a solid, that will cause the reaction rate to go more quickly as well. Think of having a sugar cube and a teaspoon of sugar and dissolving them in some tea or coffee. The teaspoon of sugar will dissolve much more quickly because of the larger surface area. The same thing applies in a chemical reaction with a solid and something else. If you can powder or break up the solid, it's going to react more quickly. And then we have these things called catalysts. Catalysts increase reaction rates by lowering the activation energy. The activation energy is kind of the bump of energy that something needs to go over in order for the reaction to happen. There is a video in one of your homework assignments about catalysts that when you get to that problem, you should watch that video. And I'll talk a little bit more about catalysts on the next slide. So you'll have to flip back in your notes again. This was slide 12 in your notes, but I just wanted to bring up the topic here again because we didn't talk much about it in slide 12. But activation energy is the energy that you need for a reaction to happen. It's this little bump in energy right here. And you might notice that in a spontaneous reaction, that activation energy is quite slow, or quite low. In a non-spontaneous reaction, that activation energy is quite large. If you think of striking a match, then the match burns. That match burning is an example of a spontaneous reaction. Once you get it going, the match will burn, and the fire will go on its own. But in order to get it to burn, you had to put some energy into it. You had to strike the match against something. So that's an example of some activation energy and a spontaneous reaction. We have enzymes in our bodies that help all of our chemical reactions in our bodies to happen. Without these enzymes, the reactions in our bodies would be much too slow for us to stay alive. So these enzymes speed up chemical reactions in our bodies, and enzymes are very specific to certain substances. Here's an example. There's an enzyme called carbonic anhydrase, and what carbonic anhydrase does is it removes carbon dioxide from the blood by binding it to water. Now, carbonic anhydrase will only work with that carbon dioxide. However, each molecule of carbonic anhydrase will work with multiple molecules of carbon dioxide. So we say that it has a turnover rate of 10 to the 6th power. What that means is that one molecule of this enzyme can cause 1,000,000 molecules of carbon dioxide to react in each second. Again, some terms to know, and it would be a great idea to go through your textbook, look up these words, perhaps write down the meanings of these words so that when we talk about them in class, you'll have a better understanding of what they mean. For right now, the ones that we are going to talk about are these first ones right here, and then we'll be done for today, and I will see you on Wednesday for the rest of the notes on Chapter 5. Reactions can be identified in various ways, and one way that we can identify different types of reactions is by looking at what happens with the molecules. So we have three things that can happen with molecules. The molecules can from two or more different substances can go together to make one big substance. That would be called a synthesis reaction. And here you see an example of a synthesis reaction where there are many amino acids going together to form one big protein molecule. The molecules might be breaking apart. That would be called a decomposition reaction. An example of that is a large starch molecule breaking up into individual glucose molecules. And then the molecules can switch places. So that's called an exchange reaction. In this case, we have hydrogen and chloride here, magnesium and hydroxide on the second reactant. And the partners basically switch places. So the hydrogen goes with the hydroxide part to form water, and then the magnesium goes with the chloride part to form magnesium chloride. That's called an exchange reaction. There are 4 reactions here. Use the information that I gave you on the last slide. Pause the video. See if you can identify these as synthesis, decomposition, or exchange reactions. Here are the answers. The first equation was a synthesis reaction. That was quite easy to see that the 3 magnesium atoms and the 1 nitrogen molecule were combining to form a big molecule of magnesium nitride. The next reaction is an exchange reaction. You notice the chlorine here, it is now over here with the M, and the F, the fluorine, is now there. So the chlorine and the fluorine switched places in an exchange reaction. The bottom left reaction is a decomposition reaction. It might be a little bit hard to see from the molecular drawing, but if you look at the equation below it, you'll notice that you have H2O2, which is the chemical formula for hydrogen peroxide, breaking up into liquid water and oxygen gas. And this is what happens when you pour hydrogen peroxide on a cut. The disinfectant property happens because that oxygen is a good disinfectant, and those bubbles are helping to disinfect your wound. If you take hydrogen peroxide from your cabinet, pour it on your cut, and nothing happens, that's because it already decomposed spontaneously into water and oxygen. And hydrogen peroxide will do that. The way that we prevent it from doing that is we store it in a brown bottle because light speeds up the reaction. And oftentimes in the chemistry lab, we store our hydrogen peroxide in the refrigerator. I don't recommend that doing at home because we should never store chemicals in any place that we have food. We have separate refrigerator just for chemicals in the chemical laboratory, of course. The final reaction is a synthesis reaction. There are 2 small molecules that go together to make this one great big one. Reactions can be reversible. An example of a reversible reaction is if you heat hydrated copper sulfate, you get the copper sulfate and the water separate. You can just add a few drops of water and the reaction will go back the other way. And there's a video link right here. If you click that, you should be able to get to the video link to see that reaction. Also, we can have a non-reversible reaction. By the way, one other thing I wanted to mention is that when you have a reversible reaction, you'll see that indicated with a double arrow. A non-reversible reaction will just have a single arrow in the equation, and this is an extremely cool video. It is the combustion of gummy bears using potassium chlorate, and it's highly exothermic. When chemists say highly exothermic, they generally mean quite explosive. So that's a fun video to watch. Okay, we're not going to talk about combustion reactions today. We'll get started on that when I see you in class on Wednesday. Hope you're having a great day. Bye-bye.